Hello, Mr. Eric, Mr. Ryan, are you right?
Make a Fury feature.
Yeah?
Fury feature.
Actually, today is the 30th.
Yes, definitely. Owie.
Okay, so what have we talked about yesterday?
Word break.
Yeah, so we are given the list of words, right? So, and then we want to find out if we can break the sentences by using the words given. Okay, so first of all, we need
Well,
to
they're not
convert.
actually sentences.
It's a string, okay? So first of all, we convert it to set because by converting the list to set, we achieve a faster one constant lookup time, right? Because using the hash table. And yesterday we talked about a depth search. Without a cache is the Buffer's depth search. The I is the index I. So we can also pass the string as parameters to represent current string we have constructed, right? It's quicker to use the index I, performance-wise, okay? By putting the cache, we are remembering the intermediate result, so we don't calculate it over and over again. This is kind of like top-down dynamic programming. Yeah, recursion is the memoization, memoization. Okay. So we use these four. We check the index n. Yeah, we iterate for each recursion call. We iterate over the next split point, right? So for example, like Eric Ryan. Also, we have another Eric Ryan. Okay, for example. So we are here. We can split with the next jump point could be here, or the next jump point could be Eric Ryan here, right? Right? So it needs to check for each index I. It needs to check if it's possible to jump to split, to the end. Yeah. So there will be n possibilities, right? So if we put a cache here, right? So that obviously there will be O n. For a string of size n, there are n plus 1 split points. For each recursion, we are iterating over the possible jump point till the end. That's O(n) here. And the substring is O(n), so the time complexity overall is O(n) times O(n) times O(n) cubic. The space complexity is purely determined by the recursion depth. For this implementation, the recursion depth is the maximum is O(n). The space complexity is O(n). So if we are here, DFS I from 0 to n, right? So there will be the recursion depth is going up to n. So we also talk about slightly different. Yeah, this one is to iterate over the index, the next split point. We can also iterate over the words in the dictionary, right? And then we check if it's possible, if the word in the list is next possible substring. If it is, then we can jump into it. It's slightly different, but yeah, the time and space complexity is the same. Okay. At the beginning, this is a search tree, so we can jump to Eric, and then here we jump to Eric to Ryan, right? So Ryan, yeah, that's Y, and then N, right? Eric, Ryan, N. Right, and possibly if we add another keyword here, it would be Eric Ryan, and possibly you could jump Eric Ryan here, yeah, okay, and then N, you see. Depth search, going down as deep as we can. Breadth search, level by level.
Deep as I can.
In order to implement the breadth search, what kind of data structure do we use to implement the breadth search?
Q.
Yeah, in Python, what exactly?
Q.
DQ, DE. What does DE mean?
Double-ended Q.
Yeah, double-ended Q. Okay. Double-ended Q. So it's a data structure which you can push and pop on both sides. So from this side will be push, will be append. And then if we want to append to the left, it will be append left. And pop by default is to take an item from the right hand side. And then if we want to take items from the left hand side, let's call it pop left, okay? The breadth search, so at the beginning, we push the root here. Take everything out from the queue, we DQ items. We push the kids back to the queue, okay? So every time we can take one item from the queue, or we take everything, and then we append, we push the kids back to the queue, okay? That's breadth search. We can use the breadth search to solve it, okay? And also, we need to use the hash set to remember the split points we have been visiting, right? So we don't need to do it again and again. So this is the same thing as the hash search. W equals set words convert it to hash set to allow a faster lookup time. Now we have sin equals set. Q equals DEQ, double NDQ. At the beginning, we start at the index 0, the first index. So while Q, now current position, we just Q dot top left. Okay, so now we need to check if current is in sin, then we continue, yeah? Because this position we have seen before, we have visited before, so there's no need to do it again, right? Because we've done it. And then if it's not seen before, then the first thing we need to add it to the set, so we know next time we don't need to do it again. So sin.add current. This is to expand the kids in the horizontal level by level. Yeah. For x in range, right? The next split point could be from current plus 1 up to the end, length s plus 1. Right, this is the same as the depth search. Right? Then we just have to check if s start with the current up to x in w, the substring is in the list. If x is equals the length x, it's reaching the end, we return true. Otherwise, we just q dot append. Append the next index will be x, right? And if we can't find any solution, this is to say we are jumping to the end. If we can't find anything, then we return false because there's no way to jump to the end. This converting the list to set so we can look up faster. Yeah, one constant time. This thing hash set just to remember the index, remember the split point. Look, Eric, Ryan, N. Okay, so we're possibly here, right? Or here. So if we can jump to Eric, or we can jump to and then jump to Ryan, so it'll be Eric here and then Ryan. And we can also do this Eric Ryan if the Eric Ryan is a word in the given list. Right? So suppose we are here, we visit Eric Ryan. Right? We visit Eric Ryan here. So the next time we jump to Eric Ryan, we don't need to do it again because we have visited the same path from Eric Ryan.
Yeah.
Okay. So in other words, right, we want to construct the sentence Eric Ryan. There are two ways. One way is Eric plus Ryan. The other way is Eric Ryan. So once we know we can construct the Eric Ryan, right, we don't need to do it again, right? Because we know we can visit here. This is the thing here. We are talking about if current in sin, we visit it and continue. Otherwise, we add it to the sin. And then we are iterating over next possible jump points. Yeah, split point. The substring is given in the list, then we check if we can jump directly to the end. Then we return true. Otherwise, we push this the next jump point x. The queue contains the index. We can also store the substrings. Right? But storing the index, the numbers, is more efficient than storing the string. This is one way. The other way will be slightly different. Okay, so it will be the same as yesterday in the depth search. For x in W, we are going through the words in the list. Then we first of all we get the length x. So we just check if s current plus nx if it's equal to x, right? And then this is the same. If nx, if current plus nx equal the length of x, then we return true. We can jump to the end. Otherwise, we just q dot append current plus nx. This method is to iterate the next possible jump points. This method is to iterate the word in the words in a given list, right? And then because if there are n words, there are n possibilities, right? And then we just have to check if we can construct a substring from the current position to the length of the words, right? And then if we can jump to the end, then we return true. Otherwise, we push the next jump point. This, yeah. So slightly different, but both are okay. The time complexity will be the same to the depth search with the minimization. Yeah. So which part is the minimization in this case? You know, with the depth search, we use the cache. Yeah, this is minimization. Depth define depth search I. We remember every I index. So, but in this depth search, how do we minimize the index I?
Notebook.
Yes, notebook. But in this particular case, which
Set.
set? Yes, seen. We have seen it before, so we don't need to continue. Yeah.
100.
Okay. So what have you learned today? One last question. What have you learned today?
Breakfast search word.
What's the problem, and then how do we
The
solve
same
it?
problem as yesterday.
Okay. What's the same problem yesterday?
Is basically
Yeah. Can you just explain to me? Okay, I'm sitting right here. So can you explain to me
so we've
what's
got
the
a thing
yeah
like this.
yeah
So let's say, so we got like a big string.
yeah we've got a big string.
And we have to break it into words that we're being given, like this.
Yeah. We start. Yeah.
Okay, so you got a given word like this.
We yeah.
West or
Some okay. So 4 words. Yeah.
it.
Okay. So 4 words. Yeah.
Yeah, so this is this, and so you break it up
Yeah.
basically.
And each word can be used as many times as you want. We don't have to actually need to use all the words, and for some words we can use as many times as we want. Okay.
But what if there's 2 words in word?
Can you give me an
And
example?
one like Eric, and Ryan, and in the
Okay. Yeah. Basically, this is the problem. Yeah. Okay.
and then in the string there is Eric and Ryan.
So the sentence. What's the sentence?
Eric and Ryan is word.
Eric,
Yeah.
Ryan. Yeah.
Yeah.
And then we're given this Eric, Ryan. Yeah, we can use it. As I said, we can use this Eric as many times
Yeah,
as we
but
want.
which Eric?
It doesn't matter. Eric. Okay. What's the solution we are talking today?
Breakfast search.
We're using breakfast search. Yeah. We're using breakfast search to search the possibilities from the root to the end. Yeah. As breath. So another example, very tricky example, is that okay, Eric, A-N-D, Ryan. Okay, so Eric and Ryan, if we are given these words, ERIC, CAND, RYAN, can we do this?
No,
No, why is that?
because on Eric here,
Yeah.
and there's no C.
That's right. Yes. Okay. Exactly. Okay. Yeah.
What if you got a C somewhere else, like there?
No. Still, we have to construct the whole sentences. We can't construct partially. Yeah. It has to be a complete sentences. Okay. Okay. So yeah. So the breakfast search. So basically, we're expanding the trees level by level. That's the difference. Okay. Level by level. Yesterday we are talking about the depth search with minimization. Basically, it's the depth search. We're using the DFSI. I is the index where we are currently at the split point. Yeah. For each index, we can break the sentence by the index I. So DFSI means that if we can break the sentence from the index I. Okay, and we use the cache. For the depth search, we are traveling level by level. So from index 0, the next possible index could be maybe 2, 3, 4, and then we are visiting 2, 3, 4, and then again level by level. And we're using the queue. For example, for some index we can visit it in many ways, right? For example, in index 4, 0 to 4 here, maybe 0, 3, 4 here. So look there, the node 0, 4 the node 4 has appeared many times, so we don't want to calculate it over and over again. So that's why we use a sim table to remember, to only calculate it only once. Yeah. Okay, that's it for today. Bye bye. Bye bye.